Okay, good afternoon, everyone. Welcome to our Telescope webinar about the use of Earth observation data and services to support flood monitoring. My name is Evelien, Communication Coordinator at Vito Remote Sensing, and today I have the pleasure to introduce Lisa Landuyt and Bram Vogels. Lisa Landuyt is a data scientist at Vito Remote Sensing. She holds a Master of Science in Bioscience Engineering with a specialization in water management. Lisa also obtained a PhD focusing on algorithm development for SAR-based flood mapping. Currently, Lisa applies her expertise to contribute to the development of Earth observation-based applications, leveraging different sensors and machine learning techniques. Bram Vogels is also a bioscience engineer. For the last 15 years, he's been working for the Flemish Environment Agency, focusing on water assessment. His expertise lies in evaluating the impact of permits on the water system. Bram is involved in the construction of new flood models and implementing drone-based remote sensing for accurate assessments during floods. Before I give the floor to Lisa, I would also like to encourage you to ask questions via the Q&A feature. Other participants will be able to upvote questions if they want to receive similar information. We will answer them in the Q&A session at the end of the webinar. And if you have any technical issues, feel free to reach out to us via the chat. Enjoy the presentation, and Lisa, the floor is yours.
Thank you for the introduction, Evelyn. Let's first start with the short overview of what we will discuss during the next half hour. We will give some context on what's happening in Flanders regarding flood control. We will then discuss how flood monitoring takes place with point-based information, discussing limnigraphs, pluviometers, and field observations. We will then go over to the remote sensing part, discussing radar-based rainfall predictions, drones, and satellite SAR data, to then conclude and give you some future perspectives. And I will now give the floor to Bram to continue.
Okay, thank you, Lisa. First of all, a slide with an overview of the flood legislation in Flanders. Like a lot of legislation, it is initiated by a European directive. So we have the European Flood Directive working on the floods. And important in this flood directive is that it says that we have to reduce the flood risk. So flood risk is not the same as a flood chance. So the flood risk is a combination of the flood chance combined with the resulting damage. So to achieve this, we can work in a three-way strategy. The first one is protection. That's the more typical technical engineering solutions. So that's construction of dikes, etc. So to prevent a flood to happen. So you're working on the flood chance. The second one is prevention. Then you're working on the remaining resulting damage. So that's to prevent that you have damage in the area. So if you're going to construct a house in a flood-prone area, you have to build it in a certain way that you don't have damage during the flood. And the last part is preparedness. So that's the prediction when a flood is coming, etc. So people who are living in a flood-prone area can prepare also that the fire department, if necessary, the military, etc., are prepared for the coming flood or the impact of the floods. And to work on these three-way strategy, of course, we need very good flood maps. At least they are crucial to have a good overview of the impacted areas. In Flanders, we work around three types of flood. The first one is pluvial floods. So that's the impact of very intense rainfall, so extreme thunderstorms. That's pluvial floods. That's more local flooding. Then we have the fluvial floods. Those are the typical bigger river systems flooding bigger valley systems. And then the third is the coastal floods. That's mostly during a northwestern storm combined with high tide on the sea. So that's in a short notice the flood directive in Flanders. To work on this three-way strategy. Of course, during a flood we need a lot of information. To achieve that, first of all, we have certain point-based information that we get. First of all, the limnigraphs. So those are situated on a lot of river systems in Flanders. Every dot you see here on the map is a limnigraph, and you also see that to the south of Flanders in the Walloon region and France, we also have limnigraphs, or we get the information of the limnigraphs, of course, to see what's coming from the south, because most rivers in Flanders are running from south to north, and here you have the Netherlands, but then water is already out of Flanders. For every point on this map, we have all information, and the point will also give a different color if a problem is measured or is predicted. So an orange color indicates that there are floods, but it's not yet a problematic flood. It's only when it's becoming red that the buildings, the first building in the valley is flooded. So from the red area, we call it a critical flood. So with probably a lot of damage. The second information, or point-based information, is the network of pluviographs. So of course, flooding is caused by a lot of rainfall. So in every point, we measure the rainfall, and we get this on a 15-minute basis. And the last point-based information is a lot of field observations. So of course, we as a water board, we have a lot of people on terrain. We also use WhatsApp, etc., to share the information that people see on the terrain, to give extra. Sorry, the slides are going forward. To give extra information to the people behind the desk, or the people who need more information about a certain point. After the flood, we also get all the information that the insurance companies get. So every house that is flooded will get in our GIS portal, which is also important to see, to compare it with our flood maps, or the regions where we expect a lot of damage. All this is, of course, point-based information. If we go to remote sensing, we, of course, have a bigger area to cover. First of all, we have the radar data. So we have at least 2 radars in Flanders, and we also use the radar data of the Dutch radar system in the north. And we calibrate this radar data based on the pluviographs. So sometimes the radar gives a little bit an overestimation of the rainfall, so we can correct that based on the point-based information we get from the pluviographs. And then the drones are quite important for us to get a quick overview of the impacted region. For instance, in this area, that's the flooded area during the 2021 floods, which had a big impact on mostly on the Walloon region, but also in Flanders and in Germany. And luckily, in the Walloon region, we also had a lot of casualties. That wasn't the case in Flanders, but anyway, we also experienced floods. And certainly, if the area is not too big, we fly this in georeferenced ortho pictures, so we can immediately incorporate the pictures in the GIS systems, and also we can follow the flood. So in the first image, you see that a part of the city center is flooded. 1 hour later, you also see that almost the whole city center is flooded. The fire department is trying to hold the water here. But in the last picture, you see that also this last line of defense is, the water is running around it. So that's lost. This information overview is quite important for us, because also our people on the terrain, they see it from where they're standing. We also have the measurements, but we need a good overview also to give all the information to the fire department, etc., for the houses which are impacted. The good or easy thing with drones is that it's very flexible. So we try to get the drone above the river system at the peak water level. So here these 2 dots are when the drones were flying. And it's in this case, it's a river system which reacts very fast. So if you are 1 or 2 hours later, yeah, the water level will be down by half a meter or more. So in this case, we only missed it by 2 or 3 centimeters. That won't be visible on the map. So that's the easy thing of using drones, that it's very flexible, but of course the area to cover is much smaller than with other remote sensing. If the area which is impacted is bigger, it's not possible anymore to fly it in georeferenced ortho pictures. We will use video data to fly all our valley systems to get a good overview of the impacted area. All right, Lisa, I think the next slide is for you.
Yes, indeed. Then we'll go over to a third source of remote sensing data, which are SAR, or synthetic aperture radar satellite data. Let's see if the slide now wants to go on to the next. Yes. So for those of you who are not familiar with this type of data, so SAR sensors are actually active sensors. So where the more familiar multispectral sensors use the energy of the sun to capture actually the amount of this energy that is reflected by the Earth's surface. SAR sensors actually send out a signal themselves, so actively, to the Earth's surface, and they then measure the amount of this signal that is reflected back to the sensor. This is what we call the backscatter. And it's actually due to this active character, as well as due to the wavelength, which is longer than in the visible spectrum, so it's in the microwave spectrum, that we can actually see through the clouds. Like you can see on this example, we have here 2 satellite images, one from Sentinel-2, one from Sentinel-1. And on the Sentinel-2 image, you can see that it was actually clouded that day. But on the Sentinel-1 image, we can clearly see the flooded area in dark here. For those of you who don't know Copernicus, so both Sentinel-1 and Sentinel-2 are Copernicus, so the European Commission's Earth Observation Program constellations. Both of them are providing global data sets that are open access to all. And with Sentinel-1, actually, we had a constellation of 2 satellites, Sentinel-1A and B. But unfortunately, there was dysfunctioning with Sentinel-1B in the end of 2021. So we're only having 1 satellite now, which is causing the observation frequency to have decreased a bit. In general, there is a repeat frequency of 2 to 3 days. Currently, with only 1 Sentinel-1 satellite, we're between 1.5 and 8.5 days for Flanders. But so, as I said, the SAR sensor is actually measuring the amount of the signal that is reflected back to the satellite. So that's the backscatter signal. And the strength of this signal is actually depending on what's present on the Earth's surface. You can see it represented here a bit. So in case the surface is very smooth, specular reflection will occur and only a very small amount of the signal will be reflected back to the sensor. This is the case for water surfaces, but also for other very smooth surfaces like asphalt. In case of buildings, a phenomenon called corner reflection takes place. So the signal will be reflected twice, as you can see, and this will result in a very bright pixel, so a very strong signal. For the more the rougher land, let's say, diffuse scattering takes place, while for trees or for snow, volume scattering takes place. And this results in intermediate signals, so also intermediate brightnesses in our image. And it's by taking into account these phenomena that we can actually try to interpret these SAR images. And so what we actually did in collaboration with the Flanders Environment Agency, we developed an automated algorithm to delineate flood extent on these images. And I just want to make the side note here that if you look at algorithm development for SAR-based flood mapping, but I think in general in remote sensing algorithms, that there's these two categories. There's the global approaches on the one hand that are really developed in order to be applicable across the globe. So they need to be very robust, need to be general applicable, and they need to rely only on global data sets. In Flanders, though, we have a lot of very detailed local information. So we really chose to make a more locally tailored approach to be able to optimally use this locally available information and also adjust to the local end user needs and to the local scale we have in Flanders. So we developed this local approach. If you're more interested in global algorithms, I can refer you to the Copernicus Emergency Management Service, who has a global flood monitoring product as well. Now, some words on the algorithm that we developed. So it's a change detection based algorithm. It uses a pair of two SAR images. And we also use ancillary information like land cover, elevation, and flood risk. And then we actually have two parallel workflows, let's say, one that works on the pixel level, and the other one first groups similar pixels into objects to then classify these. And we do this because actually both approaches have some complementary strengths. We then combine the outcomes of both workflows, and that results into this final flood map, of which you can see an example here that has 8 classes. So there's permanent water, there's clear flooding, there's more onshore flooding, there's long-term flooding. Then we also detect flooded vegetation. And then we infer, because C-band SAR cannot see through the canopy, so we cannot say anything about the flood state below or close to trees and forests. But based on the elevation, the land cover, and the flood risk maps, we do infer some kind of probably flooded forest class that you can see in green. Okay, maybe it's time to go over to some examples. Here you can see actually how the point-based observations that Bram already mentioned relate to the SAR-based flood maps. So some of you might have read or heard that we had quite some flooding, severe flooding in the west of Flanders in November, past November. And here you can see actually on the left, the water level measured on the IJzer River, while on the right, you can see the corresponding flood maps. So the red dot on the left shows you the Sentinel-1 acquisition dates, while the red dot on the right shows you the location of the water level. So you can see we have very detailed information on a single point with the point-based water level sensor. With the SAR sensor, we get less accurate but more spatially contiguous observations. You can clearly see here how during these 2 months, the valley gets fully filled and then empties a bit again. A bit less long ago, January this year, we also had quite some flooding in Flanders. And here you can see how SAR data can give us a nice overview in a one shot. So you see here the observed flood extent on the 6th of January in the morning. You will see this black line showing the edge of the image. So we don't have any information about the other east part of Flanders here, but you can really see how there's flooding present in actually all provinces of Flanders at this time. But also smaller flood events can be captured. Here are just 2 examples. On the left, you can see a flood map for the river Mark and Dender in the winter of 2021. While on the right, just 2 weeks ago, this didn't get the news, of course, but you can see that upstream of Mechelen, there was quite some flooding also present along the Dijlen. Then we also have some what we call derived products, so products that are being calculated from the flood maps. So what you can see here is the maximal observed flood extent, so the maximum contour for Flanders between the 1st and the 8th of January this year. So as you could see on the example some slides ago, We didn't have any information for the east of Flanders. While here, by combining different observations, we can give an image of the entire Flanders, and also some water levels reach their peaks on other times. So this is all aggregated here. We also have a product providing information on the flood duration. So here we're going back to the flooding of last autumn at the IJzer River, where on the left you can actually see the deduced flood duration on the pixel level then for the basin. So you can actually see how many days a certain location was flooded throughout these 2 months. Of course, as we don't have observations every day, there's an important uncertainty to be taken into account here. So that's what you can see on the right. We can only see if a pixel was switching from flooded to non-flooded, but we don't know what's happening in between. So it's important to also consider this uncertainty when looking at the flood duration. But you can clearly see which pixels were flooded for a longer time and which were just flooded for a few days, for example. A third product we have are the flood occurrence or recurrence maps. So these are just 2 examples showing the amount of time every pixel was observed as flooded throughout a period of 5 years. We're looking at 2015 to 2020 here for part of the IJzer River on the right and part of the Demer Basin on the left. So this is actually some kind of remote sensing based flood risk, you could almost say. Although there is an important bias here because we don't observe every day or every hour. So there's some areas or some floods that we can miss. And also there are some areas, for example, here you see this discontinuity in the valley here. But this is a forested area where we cannot observe floods. So this map also only shows floods that were observed. So floods that a SAR image can observe, and also floods that were captured by the right overpass. So something that you can put next to a flood risk map, but definitely not to be strictly interpreted as such. Okay, so maybe also good to highlight some limitations, especially in the Flemish context. First of all, urban areas, because of the strong signal that we get from buildings, you can clearly see the bright spots here for all the built-up areas, combined with the coarse resolution of, or the medium resolution, let's say, of Sentinel-1, which is 10-meter pixel spacing. It's very difficult, let's say, impossible to detect urban flooding. Just to show it here, this is an image of the 15th of July, 21. I guess most of you know that there was some extreme flooding going on then in Pepinster and Verviers. But as you can see here on this example, we couldn't observe this through Sentinel-1. Another limitation I already touched upon are the forested zones. Here, just an example to illustrate it. On the left, you can see a drone image, and due to the high resolution, you can really see the individual trees and the floodwater standing below. On the right, you can see the Sentinel-1 image, where you can see the very dark areas representing the flood extent. But for this flooded forest, it just has the brighter signal that we expect from a forested area. And then finally, especially in Flanders, there's a lot of small or very shallow or highly dynamic floods. If there's no overpass of the satellite, we of course cannot capture it. And with that, I'm going back to Bram.
All right, thank you, Lisa. Maybe a short clarification of how we use the data. First of all, we use the data, certainly drone data during crisis management. To have a good view on what's going on the terrain, and it's also we can also get a live stream if necessary. But in the more after the floods or after the crisis situation, we also use the data to validate the model output. We can compare what we've seen in the drone images you see on the right, and compare it to the flood maps we create with our flood models, which you can see to the left. And in this case, of course, the flood contour observed on the terrain is quite the same like we modeled. So the conclusion is that the model in this area is fit for purpose, or is very good. It's also interesting to see if we can see if the satellite or the algorithm that Lisa was talking about creates correct flood maps. In this case, it's going forward again on its own. In this case, you see here a big gap in the flood contours. And if you see on the drone images, you see that there are a lot of fruiting trees in the flood-prone area. So apparently the algorithm was missing these fruiting trees. So you can adjust it in the algorithm. And so you can increase the perfection of the algorithm. Of course, these fruiting trees shouldn't be there in a flood-prone area, but anyway, they're there. So we need to know that the area is flooded. Satellite is for us quite interesting to get a good overview of the totally affected area, and like the point-based information is on a certain point, the drones are on a certain heavily impacted area, but we can't use a drone in the totally flooded province. So the satellite image also gives information about the less crucial area. So that for us in an operational way of working, that's quite interesting to have. And if you compare the drone-based observations with the satellite-based observations, of course, these drones are very flexible. We do a lot of flights during a flood event, and we can direct the drones when the peak of the water level is at a certain point. Compared to the satellite-based observation, you have a much lower frequency, and you can't say we need an image at 2 o'clock in the afternoon. So that's possible with a drone, not with a satellite. Drone has the disadvantage of being just a small area of interest. I think we fly about 300 to 400 hectares an hour for ortho pictures, and in video around 1,500 hectares. But the satellite, of course, covers the complete area. The drone images have a very high resolution. 1 pixel is about 3 centimeters, while satellite-based observation, like Lisa already told us, is 10 by 10 meters. Drones comes with a certain cost. Of course, someone has to fly for us and has to guarantee that he can be anywhere, wherever we say he has to fly within 1 or 2 hours. While Sentinel is free to use. Of course, you can have some costs to construct the algorithm, etc. But normally the data is available for free. A drone, of course, is weather and light sensitive. With very, very heavy winds or very heavy rainfall, it's impossible to fly with a drone. And we're now testing if it's possible to fly during the night with a drone and some adaptations. That looks promising, but it's much slower. Compared to the satellite, that one is of course weather independent. And the drone-based observations, they give us real-time information. We also can have a live stream, so if it's very critical at a certain location, we can see live with the drone. Of course, the satellite-based observations, they have a certain delay, and you need a post evaluation. So they all have their pros and cons. So not one information is the most important one, but I think it's the combination of a lot of information sources, which is important, not only drones and satellites, but also the point-based information, etc. So you need a lot of information sources to follow the flood, and also to do a post evaluation after the flood. I think, Lisa, this is again for you.
Yeah, Thank you, Bram. Yeah, so if we sparked your interest and if you're interested to get your hands on the data, some information on where to find it. First of all, for the point-based information and the radar data, you can find everything on waterinfo.be. You can see the screenshot here, also the limit graphs that Bram showed earlier. And as you can see, there's also more than just flood information there. There's also information on drought, on water quality, and so on. Not yet there, but coming soon is information retrieved from the drone data or the drone data. So keep an eye on Waterinfo for that. If you're interested to look at the Sentinel-1 images we showed, then we're happy to refer you to the Terrascope viewer, so viewer.terrascope.be. You will find the Sentinel-1 SAR data here. You can easily scroll through time, compare dates, and so on. And you will also find the multispectral Sentinel-2 data and several other data layers. The Sentinel-1 maps, if you're interested, you're free to contact us. That's currently on request. And to end, I would like to share some of our future perspectives. So we aim to continue the work on the Sentinel-1 based flood maps, more specifically to improve the computation efficiency so we can provide faster maps, especially in times of crisis, and also facilitate the access. And then our other two focus areas for the future are drone imagery, more specifically to automate the workflows for this type of data and to also automatically map flood extent for these data. And then secondly, we're looking into commercial SAR imagery. Just to show you an example here on what that data can mean. On the left, you can see a Sentinel-1 image acquired for the village of Vintelen next to the IJzer River, where we had the severe floods in November. On the right, you can see 3 acquisitions that were made by Capella Space. So there's actually 2 advantages of these type of data. First of all, you can clearly see the improved spatial resolution. And then secondly, these data are acquired based on flexible tasking. So it's not as precise as with a drone image where you can really say we want an image that hour and that precise footprint, but you can task an image to be acquired within 24 hours, for example. But then there's also quite some challenges related to this data type that we want to look into. And we will do that in the context of the FLOWS project, which is a recently approved project, a BELSPO project. So more coming on that in the future. And with that, I'd like to thank you for listening. And if you have any questions, we're open to answer them.
Yes, thank you, Lisa and Bram, for this clear presentation. There's already a few questions that are coming in. The first one is about different band radar. The question is, could P-band radar data help improving the predictions, for example, in forested areas?
Yes, good question. It's indeed true that the wavelength kind of determines the scale of interaction. So the longer the wavelength, the longer, the bigger the objects will be that there will be interaction with. And indeed, longer wavelengths, there's, for example, L-band sensors, like the ALOS sensor, that have shown that you can map floods in the Amazonian forest, for example. So we're very much looking forward actually to the launch of the NISAR mission. That's, if I'm correct, scheduled for March already, because that mission will also acquire, it will be a dual wavelength mission and will also acquire imagery at the longer wavelengths. So that might help us improve the detections for forested areas indeed.
Okay, thank you. Another question, this is more for Bram, I guess. Could you elaborate on how your drone-based data mapping supports the government and local stakeholders on the crisis management.
Yeah, first of all, we are the water board, so we have to manage the flood ourselves, and it's because we had a big need to get a good overview of the flooded area. So that's the first thing which is very important for us. Also, we can have a good check of everything is okay in the river system or the river basin. Like during the last floods, we saw obstructions in the river, etc. So we can direct people to that area quite quickly. So that's information you quickly get from a drone image. The thing is, we're now working on making the drone images available on a quick way to all the people involved in the crisis management, so that they can use the images when they want to. To increase the use for other people too, and also on the with a big flood, you get these provincial crisis teams, etc., and there we can use these images to evaluate what's going on the terrain. Where do we have to build an emergency dike? Is a fire department pumping in the right direction? Things you can easily see on these drone images, because also the fire departments, they complain that they just have local information and they just need an overview. So a lot of stakeholders in this crisis management are looking for these good overviews of the impacted area. So that's during the crisis management, and of course after the crisis management, you get a lot of stories about people, how it was going on during the crisis and where water was flowing. But now we can check it very easily on the drone images what was going on. So also to exclude fairy tales that sometimes evolve during flood-prone floodings. So it's during the crisis and after the crisis that it's very important for us as a water board to have these images.
Okay, the questions for Bram keep on coming. Do all insurance companies contribute to reporting damages, or only selected companies? And if so, at which resolution are they reporting on individual addresses, or do they give you statistical aggregated statistics?
First of all, we asked very nicely if they wanted to contribute information. That was a no. So then we put it in the legislation that they had to give us the information. So now they are giving us the information on individual address basis. Of course, this is information which we can't distribute because it's privacy sensitive, of how do you call it in English? Anyway, but we have the informations for ourselves and to validate the flood maps.
All right. Another question. Would it be possible to lower costs for monitoring? You had tactically placed drone in a box systems and autonomous drone flights, whenever that is allowed by legislation. Do you think that would be a cost?
Sorry, Jürgen, the sound was gone. Do you still hear me?
I think it will be better that Evelien takes over because I have an unstable connection.
Anyway, I understood the question, but I think the most important is, if the current legislation changes, of course, now it's not yet possible. So we fly as a state flight because we're involved in crisis management. So then a lot of legislation could be neglected, but of course we want it to happen as safely as possible. So we see that they also have to keep a line of sight to the drone, etc. So until now, someone has to be on the terrain with a drone. These drones in a box, we'll see what the costs are of this system. I haven't seen any cost yet for it. Of course, these drones we fly in during rain, during heavy wind too. It's not nice and sunny when it's flooding most of the time. except in July 2021. That was pretty good weather after the flood. But most of the times, yeah, it's pretty adverse weather. So we also need drones in these boxes which can endure rainfall, very heavy wind. So I think there are still quite some challenges before that system is interesting for us, I think. But anyway, if they're good proposals, we're happy to hear about it.
Right. I think we've covered the questions that came from the public. I have a few ones for the both of you. Lisa showed these SAR-based flood products. Which ones are the most valuable ones, do you think, Bram?
Sorry, can you repeat it one more? Because I saw another question coming in, Jürgen, that I was reading
the
that one.
SAR-based flood products that Lisa showed, the flood extent and the flood.
I'll take over. The SAR-based flood product, which ones are more valuable?
For us, I think it's a maximal flood contour to get a good overview of the last days, yeah, where the problems were or are still on the terrain. And of course, in post-processing, of course, flood duration, flood frequency, certainly if you can evaluate a lot of years with yeah, SAR-based images, I think the maps will be becoming more and more interesting in the future. The more data you get, the more you can say about yeah, flood frequency, etc. So yeah, we're looking forward to the future.
Okay, and indeed, we received a new question in the Q&A, which if elevation data is used in the modeling as current rain and surface models in Flanders are quite old.
Yeah, we still use the second digital terrain model. So I think the acquisition of the data was somewhere in 2015. Yeah, in that region. Yeah, it's quite old, but it's not that we yeah, dig out Flanders every 5 or 6 years. So of course, locally, there can be a difference, but in general, in certainly in these bigger valley systems, the new DTM won't have a big impact. Only on a very small scale you can have some changes. But anyway, once there is a new digital terrain model, of course we will remodel our flood maps with this new basic information.
Okay, just 2 short ones before we close. Here's another one that came through the chat. Contributions from the public to derive flood extent. How do you know that it is reliable?
I suppose that's also a question for me. Yeah, most of the times we only use the information yeah, we gathered ourselves, or where there is yeah, a picture, a video, etc., or an official organization like the local municipality, etc., also guarantees that there was a problem. So to get some yeah, objective information in between. So yeah, we don't take every thing that a civilian says for granted, but most of the time it's of course correct, and most of the time they have pictures, so okay, there's no discussion.
Good. Then one last about TerraFlood. Is it applicable everywhere? What ancillary data is needed for a good result?
Yeah, so the ancillary data we use are elevation, so digital terrain model, land cover, and flood risk. Where I can add that the flood risk layers are mainly used to limit over predictions of the uncertain class. So we have the clear flooding class and the more uncertain flooding class, as well as for the probably flooded forests. So in theory, the model could also be applied without these ancillary data, but the maps will be more uncertain and be less informative, especially with respect to the flooded forests.
Okay, so no other open questions. So thank you, Lisa, Bram, and Jurgen, for the interesting presentation and discussion. Before we close this webinar, I would like to show the upcoming webinars. More information and registration and also other webinars are available on the Terrascope website, so feel free to check it out. And that brings us already to the end. Thank you all for joining us. We hope to see you in one of our next webinars, and stay in touch via the website. Subscribe for our mailing or follow us on social media. Have a nice evening.